Good morning. Now, in today's session, we will learn about radius of gyration. So, radius of gyration, yeah, you might have heard about this term when you are doing compound pendulum experiment and all, right? So, let us see what is meant by radius of gyration. In the last class, we have already seen that moment of inertia of a body about an axis of rotation is I equal to sum of masses, that is sigma m into r square. What is r? Perpendicular distance from the axis of rotation. Okay. Now, if you assume that the entire mass of the body is concentrated at a point at a distance k from the axis, then moment of inertia can be written as I is equal to sigma r square equal to mk square. That is, sigma m is replaced with the capital M and r square is replaced with the k square, where m is the mass of the body, k is the radius of gyration of the body about the axis. Thus, radius of gyration is denoted by the letter k, and it is defined as distance from the axis of rotation, the square of which when multiplied by mass of the body will give the moment of inertia of the body about that axis. Okay. So, k is the radius of gyration and it is nothing but distance from the axis of rotation, the square of which when multiplied by mass, that is mk square, will give you moment of inertia I of the body about the axis. Okay, so that is what the whole paragraph you have to write when you are asked to define radius of gyration. Okay. Next is rotational kinetic energy of a rigid body. We know any body in motion possesses kinetic energy, right? Similarly, a rotating body also possesses kinetic energy because of its rotational motion. Now, this rotational kinetic energy depends on other factors, two factors, which are the mass of the body m and angular velocity, that is rotational kinetic energy depends on mass of the body, angular velocity omega, and distribution of mass points about the axis of rotation, that is r. Okay, so rotational kinetic energy depends on these three factors: mass, angular velocity, and distance from the axis of rotation. That is same as distribution of mass points about the axis of rotation. Okay, so if a rigid body, as I already said, if it is composed of point masses m1, m2, m3, etc., which are at a distance r1, r2, r3 from the axis of rotation, and suppose that they are having linear velocity v1, v2, v3, then what will be the expression for rotational kinetic energy? It will be T is equal to half m1 v1 square plus m2 v2 square plus m3 v3 square. Okay, that is equation 14. Now R1, R2, R3, what are they? They are perpendicular distance from the axis of rotation. Okay. Now we have already discussed in our first class that all the point masses will possess same angular velocity omega. Okay. So we can write the linear velocity of point mass 1 as v1 equal to r1 omega. Now linear velocity of second point mass, it will be v2 equal to r2 omega. See, but omega is the same for all point masses. Why? Because all point masses possess same angular velocity. So our equation 14 can be written as like this, that is half m1, instead of v1 just write r1 omega r1 r1 omega. So v1 square will become r1 square omega square. See, like that you have to modify equation 14. So your equation 14 will now become 14a. Now using the definition of moment of inertia, we can reduce equation 14a as t is equal to half I omega square. How do you get that? Because you know m1 r1 square, m2 r2 square, m3 r3 square. That is, all these are expressions for I, moment of inertia, because moment of inertia is I is equal to mr square, right? So you just replace those m1 r1 square, m2 r2 square, m3 r3 square with I. Then what is remaining is omega square. That is how you got this expression. So T is equal to half I omega is your expression for rotational kinetic energy of the rigid body. I is the moment of inertia and omega is the angular velocity. Okay, rotational kinetic energy is represented by the letter, capital letter T. Now let us see. So this is what you have to write when you are asked to write about rotational kinetic energy. Okay. Now this is an analogy between rotational and translation motion, just a comparison. This is also very important. In rotational motion, what we use is angular. Okay. But in translation motion, we always use linear. Okay. So in rotational motion, angular displacement is theta, whereas in translation motion, linear displacement is represented by small letter x. Angular velocity, rate of change of angular displacement with the time, that is omega equal to d theta by dt. But here it is linear velocity represented as v equal to dx by dt, distance by time. Okay. Now angular acceleration alpha, rate of change of angular velocity with the time, d omega by dt. Here it is a is equal to dv by dt, that is a rate of change of velocity with the time. Here moment of inertia I. Here we are denoting it with a small letter mass m. Angular momentum L equal to I omega. Here we use linear momentum P is equal to mv, mass into velocity. In rotational motion, we always speak about torque, that is tau is equal to dl by dt. We have already discussed about this rate of change of angular momentum with the time, right? But in case of translation motion, instead of torque, we are using the term force. F is equal to dp by dt, that is rate of change of linear momentum with the time. Okay. Now, work is integral tau d theta. Here work is integral f dx. Power is tau omega. Here power is force into velocity, Fv. Kinetic energy half I square. Here you know it is half mv square. Okay, so study this table. Just a comparison between rotational motion and translational motion. Similar to Newton's laws of motion, here in rotational motion also we have three laws of motion. First one, this is similar to Newton's first law, that is, every body continues in its state of rest or uniform rotational motion about a fixed axis unless it is compelled by an external torque. That is, here we are putting those statements in terms of rotational motion. See the difference. Instead of force, we are writing torque. Instead of linear motion, we are writing rotational motion. That is the only difference. Now, this is second law of motion in the case of rotational motion, that is rate of change of angular momentum. In Newton's law it was about linear motion, so they will be talking about linear momentum, okay, of a body about an axis of rotation is directly proportional to torque applied, and it takes place in the direction of torque. But in Newton's law for linear motion, in place of torque, what we had force. Okay. Now, third law, For every toe applied by one body on the other, there is an equivalent opposite torque. That is, instead of force, you have to write torque applied by the second body on the first about the same axis of rotation. Okay. So these are Newton's three laws of motion modified in terms of rotational motion. So make the changes correspondingly. Okay. Now these are very important theorems on moment of inertia. This is very important. This is a sure question. You will be asked either to write parallel axis theorem or perpendicular axis theorem. So first let us learn about parallel axis theorem. This parallel axis theorem states that this is a statement. Okay. Moment of inertia of a rigid body about any axis is equal to the sum of its moment of inertia about a parallel axis passing through its center of mass and like this, and product of mass of the body and square of distance between the axes, that is I equal to ICM plus MA square. That is the mathematical representation of the statement. Now let us see the proof, then the statement will be clear. Okay, it is moment of inertia of a rigid body about an axis, that is I, is equal to sum of first term. What is the first term? Moment of inertia about a parallel axis passing through its center of mass. Let that be ICM, center of mass, moment of inertia about center of mass, plus product of mass of the body and square of distance between the axes. Distance between the axes is A. Okay, so this is the mathematical representation of this statement. So let us see the proof. This is a rigid body. Consider rigid body of mass m shown in the figure. Let ICM is the moment of inertia of the body about the axis ZZ dash passing through the center of mass. So ZZ dash is an axis passing through the center of mass. So let the moment of inertia about that axis, that is about ZZ dash, be ICM. Okay, and let I be the moment of inertia about another axis, that is say AB, parallel to ZZ dash. Okay, so you have two axes. One is ZZ dash passing through the center of mass and the other is an axis AB parallel to ZZ dash. Let ICM be the moment of inertia about ZZ dash. Let I be the moment of inertia about AB. Now these two axes, that is AB and ZZ dash, are separated by a distance small letter a. Okay, everything is clear from this figure. Then according to parallel axis theorem, the one that I have wrote just now, okay, as per the statement. Now we are going to prove this. For that you have to consider a mass point small letter m located at a point P. See, you are considering a small point mass small letter m located at a point P which is at a distance y plus a from AB. See, this distance is a, this distance is y. So the distance of the point mass m located at the point P from AB will be y plus a. See, okay. Now what will be the moment of inertia of the point mass about AB? It will be mass into distance square, right? That is the definition for moment of inertia. Mass into distance square. So mass into, what was its distance? Y plus a. So y plus a square. So m into y plus a square will be the moment of inertia of the point mass that we have considered. Okay. Now what will be the moment of inertia of the whole rigid body? For that you have to take the summation of this. See, I get to sigma m y plus a square. Now expand this one. Okay. Now here sigma my square, replace it with ICM. Sigma ma square, write it as sigma m, write it as capital M, and a square, keep it as such. Now this one, 2 is a constant, a is also a constant, take it outside, rest is kept as such. Okay, now which is the sum of moment of all point mass about an axis passing through the center of mass. Now this will add to give you the sum as 0. So substituting these results in the above equation, that is, we just substitute all these results in the above equation, we will reach at the final expression for parallaxis theorem, I equal to ICM plus MA square. Okay, so this is parallaxis theorem statement, figure, then the rest everything is proof, and finally the mathematical statement. Now if you are asked to just state parallaxis theorem, what you have to write is, you just write this paragraph and write the final expression, I equal to IC sum plus MA square, and explain what each of these terms are. That is enough. Okay. Now if you are asked to prove it, then you have to write from the beginning. That is, write from here to here. Okay. Next is perpendicular axis theorem. It states that moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to the sum of its moment of inertia about two mutually perpendicular axes lying in the plane of lamina intersecting each other, where the perpendicular axis meets the plane. That is, I equal to Ix plus Iy. That is sum of two moment of inertia. This is the expression. See, Iz equal to Ix plus Iy. See. Okay. So if you are just asked to state perpendicular axis theorem, you just write the statement and write the final expression as Iz equal to Ix plus Iy and explain what each of these terms are. That is enough. If you are asked to prove it, then you have to write from the beginning till here. Okay, now let us study the proof. Consider a rigid body. Okay, here you are considering a plane lamina. It is just a plane for considering or a reference plane. Okay, so let z dash be an axis perpendicular to the plane of the lamina and passing through a point O. Okay, see, as already said, z dash is an axis. It is perpendicular to this plane. Okay, and it is passing through the center O. Okay, it is clear. Now, here you can see two more axes, which are the xx dash and yy dash. They are nothing but two mutually perpendicular axes in the plane of lamina intersecting each other at the point O. See, they are intersecting with each other, right? The point O. Now, let the moment of inertia about xx dash be Ix. Let the moment of inertia about yy dash be Iy. And let the moment of inertia about z dash be Iz. Okay. Then according to our parallaxis theorem, according to perpendicular axis theorem, this Iz, that is moment of inertia of plane of lamina along z dash, that is Iz, is the sum of the moment of inertia of the plane of lamina along xx dash and yy dash. Okay. Now to prove this, just consider as before a particle on the plane lamina of mass m which is located at a point P. Then moment of inertia of the particle about z dash is given by m op square. M is the mass of the point mass and op is the distance of that point mass from the center. So it is op square. Op square is nothing but, as per the figure, it is x square plus y square. Okay. Now the moment of inertia about z dash will be given by sum. Az will be equal to sum of this, that is sigma of m x square plus y square. Expand it, it will reduce to Iz equal to Ix, this is Ix plus Iy. This is perpendicular axis theorem. So these two theorems are very important. Okay, so this is definition for radius of gyration, definition for rotational kinetic energy, difference between or comparison between rotation and translation motion, laws of motion in terms of rotational motion, then parallel axis theorem proof, perpendicular axis theorem proof. Among this, all are important, but the most important one are these two theorems, parallel axis theorem and perpendicular axis theorem. Okay.